Hi, we are the team number 4 and our experiment is to check the first law of thermodynamics.
The materials we're going to use are a Chloralex container. This container has 2 hoses, our thermo book, this extension, and these 2 pumps. In these 2 pumps, the water enters here and the pump it out here. And these 3 thermometers to measure the temperature. We have 2 inlets here where the hoses are connected, and we have an outlet, only one, where the water will flow.
We are ready for start to the experiment. Here we have 2 waters with different temperatures. Here you can see that are 8 degrees, and here we are in 56 degrees. So here inside the buckets are the pumps. So we are ready to start with the experiment. The pumps. You can see how the water is working here, and now how it's going out to our steady flow process. So we're going to need the temperature.
We wish to prove if our pump is correct. This pump says that its max flow is 20.6 liters per minute, and we show if it is correct. So
I am going to take the time.
And I'm going to start the experiment. 1, 2, 3.
The time and the pump.
What we're doing here is we're checking the power that the pump requires to operate. So here the pump says on its label that it requires 127 volts of power to be function. So what we're doing here is we're checking that from the current we get 118.5 volts. But when we check what is the power that rests from when we get the current goes through the pump and comes back, we get 21.2 volts. So here we can check that the pump is actually just using 100 volts instead of 127 as it says on the label.
Proceeding with the calculus, we have the energy conservation equation in which we can see some of the assumptions that we made in this experiment. We don't have any kind of heat interaction within the boundary and the environment of the system. That's why we crossed out the Q in and Q out. Then we don't have any shaft or electric work or any other sort of work in our system, so that's why we don't have workout, but we actually have the working of the pumps that are pumping the water into the system. Then we have the summations of the mass flow rates times the internal energies, in which we only focused on the enthalpy instead of the kinetic energy and potential energy, because in this case their values can be neglected. We have a steady flow system, that's why we cross out this term and it's 0. Proceeding with our solution for the mass flow rate, we have this equation. We have the total power of each individual pump. We have the mass flow rate of the first pump times the enthalpy of the first bucket, which is corresponding to 7 degrees Celsius. Then we have the mass flow rate 2 and the enthalpy 2 corresponding to the second bucket, which is 56 degrees Celsius. Then we have the mass flow rate 3 or the mass flow rate out times the enthalpy 3, and that equals 0. It's important to note that the enthalpy 3 corresponds to the enthalpy of the bucket that received the outcoming water from our system. So then we solve for the mass flow rate out, and we obtained a value of 0.69 kilograms per second of the mass flow rate. But we wanted to compare with the actual values, the real values that are provided by the pump, instead of the ones given by the label. So the label in the pump says that it has a volumetric flow rate of 20 liters per minute, but experimentally we actually found out that it is 50 liters per minute in one pump and 15.8 liters per minute in the second pump. By obtaining the mass flow rates with these volumetric flow rates and substituting those mass flow rates in the equation, we obtain an experimental mass flow rate out of 0.5299 kilograms per second. By doing the percentage of error equation, we by subtracting the mass flow rate out from the mass flow rate out experimental, dividing it by the mass flow rate out in the calculus, we obtain a percentage of error of 23.73%.
We got a 75% of accuracy because our pump says 20.6 mass little per minute and the real was 15 to 50.8. And in this experiment we can prove the first law of thermodynamics: the mass flow in is equal to the mass flow out.